All right, so we're on problem 7, the final problem of the practice exam. And in this problem, we want to find some error bounds for our approximation techniques. So we're using the midpoint rule and Simpson's rule, and we'll do the error bounds for both of those approximation methods. And so let's just first of all recall the formula for our midpoint rule error bound. Right, so first of all, the error for the midpoint rule, this is of course just the exact value of the integral, which we did compute, and then minus the approximate value that we're getting for whatever number of intervals that we're using. So here we want to try and determine how many subintervals we need to guarantee this particular degree of accuracy. So if you're still looking at the work from the previous problem, you should see that Simpson's rule was actually really close to this degree of accuracy already. We probably won't need many more subintervals to guarantee just slightly more accurate approximation. But for the midpoint rule, we were a little bit further off, so we'll probably need several more subintervals. But either way, our midpoint rule error bound is just, well, okay, so this is the absolute value of the error in our midpoint approximation, and this is just always less than or equal to k, we'll talk about that in a second, times the length of our interval, so that's pi over 2 minus 0 to the third power, divided by 24 times the number of subintervals that we're using squared. And so in this case, we'll need to decide what k is allowed to be. And so this value of k depends on the second derivative of the function. So let's go ahead and just figure out this value of k, and then we'll go ahead and say how many subintervals we actually need to guarantee our particular degree of accuracy. So our function that we're dealing with is cosine of x. Right, so we need to take two derivatives. So the first derivative of cosine is just negative sine, and the second derivative is, well, the first derivative of the first derivative, so this is going to be negative cosine of x. So okay, our second derivative is, well, basically just the function, right? It's just negative the function. So what we know about so we need the absolute value of the second derivative, right? And so in this case, this turns out to be, well, it's just absolute value of cosine. I could say absolute value of negative cosine, but of course that negative sign really does nothing here. And so if you think about it, cosine's actually positive between these values, 0 and pi over 2, so really I don't even need the absolute values. So I'll just go ahead and write cosine, and then I'm thinking of values of x between 0 and pi over 2. And certainly cosine is less than or equal to 1, regardless of where the values of x are coming from. But here we actually do achieve the value of 1, so 1 is certainly the smallest value that I can use as an upper bound for the absolute value of this second derivative. And so this is true for all values of x in general, but specifically for the values of x that we're concerned with, 0 to pi over 2. So here's our bound for the second derivative, right? And this k here, which maybe I should write a k2, k sub 2, something like that. This is our bound for the second derivative, right? So we can actually set this value, k sub 2, equal to 1, right? And so that's what we'll use in this particular example. And so now we need our error, which we now have a value for k, it's just 1. Right, and then this is just pi over 2 cubed divided by 24n squared. We need our error in magnitude to be less than 0.0001. So what we'll do is, to ensure that, make this quantity, which is larger than the magnitude of our error, less than that number. So we'll just go ahead and make this less than 0.0001 and solve for n and see what we get. Okay, so to do all of that, I'm basically just going to forget about this term here. I just want to deal with this expression involving n and the degree of accuracy that I'm specifying here. And so to figure out how large n needs to be, of course, I'll divide by this term on both sides of the equation to get rid of it on the right side. I'll multiply by n squared on both sides, and then I'll take a square root. So what I'll end up with is pi over 2 cubed divided by 24 times 0.0001, and this is less than n squared, but like I said, I'll do n and take the square root of both sides. So whatever this number comes out to be, I need to make sure that n is strictly larger than this number, and then we'll have the degree of precision that we want. And so it turns out that this number, my approximation at least for the left side of my inequality, is 40.1859. So this number is like 40.2, for example, right? But certainly it needs to be larger than 40 and is always going to be a positive integer here, right? So we'll just take n to be greater than or equal to 41, and that will guarantee us our degree of precision that we specified here for the midpoint rule. Okay, so for Simpson's rule, the story is a little bit different. It turns out that it's actually the same, but in general it can be different. So for Simpson's rule, we need to recall the error bound for Simpson's rule. So this is just the magnitude of the error, right? Again, the error is still the exact value minus the approximate value. Then we take the absolute value of that, just so it's going to be non-negative. So either way, in this case, we need to use a bound for the fourth derivative. That's our k here. So with the midpoint rule, is a bound for the second derivative. For Simpson's rule, it's a bound for the fourth derivative. So maybe you want to write like a sub 4 or something along those lines. The length of the interval still appears, but with a different power. So it'd be pi over 2 minus 0 to the power 5 here. And then we divide by some factor like 180 and n to the power 4. Okay, so we need to figure out a bound for our fourth derivative, but actually in this case it works exactly the same as the second derivative, because if you think about it, with a function like cosine, you take one derivative, you get minus sine. You take a second derivative, you get minus cosine. Take a third derivative, you get sine. You take a fourth derivative and you're back at exactly the same function you started with. So all of this work here just applies to what we've been doing. So it turns out that the fourth derivative will also be bounded by 1. It's literally equal to the function, which in absolute value was equal to the second derivative. So all of it turned out to be more or less the same. So again, here we're going to use our K4 value as 1, and then we just need to set it up as we did before. So we'll have 1 times pi over 2 to the power 5 divided by 180 n to the power 4. We need to make sure that this quantity, which is of course larger than the magnitude of our error, we need to make sure that this is smaller than the degree of accuracy that we want. And so to solve for this value of n, we basically go through all the same steps, divide by that 0.0001, multiply by n to the power 4, and then take the fourth root. So what we'll end up with is fourth root of, well, pi over 2 to the 5th power divided by 180 times 0.0001. We're taking the fourth root of that, and then this needs to be less than n. Alright, so plugging all that stuff into the calculator, right, we get that the left side of this inequality is roughly 4.8. So this left side is roughly 4.8. We know our n needs to be even, so 5 won't quite do it for us. So as long as we take this value of n greater than equal to 6, remember it needs to be even because for Simpson's rule we need an even amount of subintervals to actually perform that approximation. So either way, n greater than equal to 6 will definitely get us the desired degree of accuracy. Alright, so that does it for the first practice exam. I hope videos were helpful. Hope they answered some questions. Of course, as always, if you have any other questions, contact me. Alright.